Hello students, welcome to Math Center Web Coaching. In our last video, we have seen how to find out the inverse of the given matrix by using the adjoint method. Now, in this video, we are going to see what is orthogonal matrix, what are the different conditions or properties of the orthogonal matrix, and some examples of the orthogonal matrix. Okay, so let's start with the definition. A real square matrix A is said to be an orthogonal matrix if the given matrix A satisfies this condition. Now, what is this condition? A into A raised to T. That means the product of the given matrix A and its transpose, that is A raised to T. If this product gives us the identity matrix, okay, then the given matrix A is called as the orthogonal matrix. It's clear? If the product of the given matrix and its transpose will gives us the identity matrix, then that given matrix A is called as the orthogonal matrix. Okay. Now in this condition, we can take a product A into A raised to T or A raised to T into A also. In both the cases, if we get the identity matrix as an answer of the product, then the given matrix A is called as the orthogonal matrix. Okay, clear? So let's start with the properties of the orthogonal matrix. Actually, these properties are so much important in exam point of view. If you are preparing for the competitive exams, okay, then there are some examples which are based on these properties. Okay, MCQ type examples. So I'm going to take that examples also in this video. So let's start with the first property. If A is orthogonal, then A inverse is equal to A raised to T. Now in 11th standard, you must have come across with the property of inverse. What is that property? A into A inverse is equal to I is equal to A inverse into R. A. Right? So if you are comparing this property, orthogonal property and inverse property, you can see here A raised to T is equal to A inverse. Okay? But if you want to prove this, then we can prove. So for that, consider A into AT is equal to I. This is by definition, right? So what is our definition of the orthogonal matrix? Product of the given matrix A and its transpose is always equal to identity matrix. Okay, that definition I have written here. Okay, so next, multiplying both the sides by A inverse. So what will we get? We get A into A transpose is equal to A inverse is equal to I. Okay. Next, now I will take these two matrices together here, that is A inverse into A and A transpose as it is, and A inverse into I is equal to A inverse. Okay. Now what is bracketed quantity? By using this property, A into A inverse is equal to identity matrix. So this is my identity matrix into A raised to T is equal to A inverse, and this will give me A3 is equal to A inverse. So A transpose is equal to A inverse, right? So by the given definition, we can prove this. Okay. So our property first tells us that if given matrix A is orthogonal, then A transpose is always equal to its inverse, or you can say that A inverse is always equal to its transpose. So this is our first property. Okay. Now the second property: if A is orthogonal, then A inverse and A transpose are orthogonal. Okay. Suppose given matrix is orthogonal, then A inverse and A raised to transpose, that is A transpose, are also orthogonal. Then third condition, if A is orthogonal, then the value of the determinant, okay, of the given matrix A is plus minus 1. So always remember this: if the given matrix A is orthogonal, then the value of this determinant is plus minus 1. Okay. Fourth condition, if A and B both are orthogonal square matrix of order n, then A into B and B into A are orthogonal. Multiplications is also orthogonal. Okay. So let's see the example. Prove that the given matrix A is orthogonal and hence find the A inverse, and A we have given here. Okay. This is the straightforward example. I am taking this example for the students who are pursuing engineering. Okay. And MCQ type of examples I am going to take after finishing this example. Okay. So let's start. A is orthogonal matrix. This we have to prove. So for that we are going to use the given definition of the orthogonal matrix. So what is the definition? Product of the given matrix A and its transpose will gives us identity matrix. So for this example, A we have given. Just we have to find out the transpose of this given matrix A. Then afterward we are going to take the product of the given matrix A and its transpose, and if that product will gives us the identity matrix, then the given matrix A is orthogonal. Okay, so let's start. So A we have given, just we have to find out the A transpose, and transpose is nothing but interchanging rows and columns. Okay, so my first row will become my first column, second row will become my second column, and third row will become my third column. Okay, so let's start. So 1 upon 3, just a sec. 1 upon 3, this constant as it is. Now first row minus 2, 1, 2. Second row 2, 2, 1 becomes my second column, and third row, that is 1 minus 2, 2 becomes my third column. Okay, so this is the transpose of the given matrix. Now what is next step? We are going to take a product of A and its transpose, that is A into A transpose. So let's take A into AT. So A, what is A? This is my given matrix A. I substitute that matrix. Then I'm going to substitute this term A transpose. Okay. So what is that? 1 upon 3, this term, into minus 2, 2, 1, 1, 2, minus 2, and 2, 1, 2. Now I'm going to take the product. Okay, here. So this constant 1 upon 3 and 1 upon 3, this will become 1 upon 9 here, and after taking the product, minus 2, first row, first column. Okay, first row, second column, first row, third column. Then after that we'll get, what is my first? In 11th standard you must have come across with this multiplication of the matrices, right? So minus 2, minus 2, okay, plus 1 into 1 and plus 2 into 2. Okay, so we'll get this term, and then after taking 9 common from this matrix, so I'm going to take 9 common, so 9 and this 9 will get cancelled, and last we'll get 1 0 0 0 1 0 0 0 1. So this is my identity matrix. Okay, so you can see here the product of the given matrix A and its transpose, okay, gives us identity matrix. So by using the definition of the orthogonal matrix, if this product is nothing but the identity matrix, then our matrix, the given matrix A, is orthogonal. Okay, okay. Now we have to find out the inverse of the matrix. Now what is our first property? First property is, if A is orthogonal, then A inverse is nothing but its transpose, A raised to T. Okay, so what is our inverse? This transpose of the given matrix A is nothing but our A inverse, because our A is orthogonal, right? So as A is orthogonal matrix, A inverse is equal to A transpose, and therefore A inverse is nothing but what? A inverse is equal to this term, that is 1 upon 3 minus 2, 2, 1, 1, 2 minus 2, 2, 1, 2. Okay, by using first property. Okay, now next we are going to see some MCQ type of examples. Okay, so let's see some examples of MCQ type. Find the inverse of the matrix. Okay, matrix we have given here. This example is from GATE exam, last to last year, I guess. Okay, and if we follow the conventional method to find out the inverse of the matrix, then that is very time consuming. So which method we are going to use here? We are going to use our third property of orthogonal matrix. Okay, so what is the third property? The value of the determinant of orthogonal matrix is always equal to plus or minus 1, right? Now, how we are going to use this property? Just we are going to find out the determinant of the given matrix. If that the value of the determinant is plus 1 or minus 1, then that implies the given matrix is orthogonal, and as the given matrix is orthogonal, its inverse is nothing but its transpose. Okay, we are going to use that concept here. So suppose this is, I assign this given matrix is A, and now I am going to find out the determinant. So what is the determinant here? The first element here 0, so first bracket 0, second minus 1, 1. So sorry. So minus 1 into 1 minus 0, and third bracket, as this term is 0, so 0. So our value of this determinant is minus 1. Okay. So minus 1. So determinant is equal to minus 1, which implies A is orthogonal, and which implies A inverse is nothing but its transpose. So just we have to check what is the transpose of the given matrix A. So what is transpose? Interchanging rows and columns. So my first row have to my second first column. Okay. So 0 1 0. So 0 1 0. Where is the first column? 0 1 0 0 1 0 here. Now here is 0 0 1 0 no. So in first A option, just check 0 1 0 first column, second row 1 0 0. This is my second row here, the second column here, right? And 0 0 1. This is my third row. Will become my third column. So this is the transpose of the given matrix A. So A is my answer. That is A. Option A is nothing but the inverse of the given matrix, right? So we have solved this example by using the third property of the orthogonal matrix. Okay. Now, what is second question? See, for the given orthogonal matrix Q is equal to Q we have given here, right? The inverse is, now in this examples also, in this example also we have to find out the inverse, but here we have already given that the given matrix is orthogonal, right? So given matrix Q is orthogonal. So as Q is orthogonal, which implies Q inverse is always equal to QT, that is Q transpose. So just we have to check what is the transpose of the given matrix Q. Now first row 3 2 6. Okay, 3 2 6. This is my first row, and in transpose that will become my first column. So 3 2 6. First column we have to search. So 3 2 6. 3 2 6. Here see 3 2 6. Now second row minus 6 3 2. Here second column minus 6 3 2. Third column, sorry, third row 2 6 minus 3 and 2 6 minus 3, and 1 upon 7 is a constant term as it is. So within a fraction we can find out the inverse of the given matrix, given orthogonal matrix, if you know this property, right? So this is my inverse of the given matrix. So that's it for the today's video. In today's video, we have seen orthogonal matrix, some properties and some MCQ type of examples of the orthogonal matrix. I hope you like this video. If you like, please like, share and subscribe the channel. Thank you very much.